Please welcome Jawad Nasrullah. Jawad is a chip designer with expertise in chiplets, microprocessors, hardware, software, co-design, and SerDes. Previously, Jawad was the co-founder and CTO of Zglue, Inc., which is a Silicon Valley-based chiplet startup that set the direction of chiplet technology and developed a number of heterogeneous integrated circuits. Jawad is now working on his next adventure, Palo Alto Electron. Jawad has been very active with the ODSA workgroup within OCP to help catalyze the chiplet ecosystem. Before Zglue, Jawad has held leadership positions both at Intel, Samsung, Sun Microsystems, and Transmeta. Jawad holds a PhD degree in electrical engineering from Stanford University. So please welcome Jawad.
Hey, great. Thank you so much, Abram, for the invitation. So we had some great talks so far that makes my life easier. I will primarily focus on system level aspects and some high level view of testability of these multi-chiplet or multi-chip implementations. So my talk will be in three sections, but I'm going to skip the first one mostly because I'll just dive directly into the testing related aspects. And one thing you will notice that I have this terminology called system level test that's a little bit different than commonly understood. So when I refer to system level test, it really means some kind of a structural test and some basic functionality combined. And I'll finish it off with a chiplet BIST example based on some of the work that we had done at Zglue. So I'll make a couple of points though. Last time I presented a design related talk. So if you are interested in some of this, you can look at the previous MapTech presentation that I did. But here I'm putting 5 different chiplet design styles from a design perspective that we have various reasons or decision points why we go with one versus the other. But one thing I did here is I listed out the classes of tests that would be needed for successful production of these systems. And you will notice we need pretty much everything like all the way to final SLT, and even, we need to think about quality and reliability. My previous experience has been with active interposer type of 3D stacking. So some of the things that I talk about are directly applicable to 2.5D and maybe even to copper hybrid bonding. That's kind of like an upcoming technology. So you can look at my slides on the flow of chiplet-based integration, but this is the first one that I want to mention here. It's relevant. So this is my view of how the components move through a manufacturing line, and then what are the important ops and test considerations. So on the left side, you see a bunch of components, some chiplets that might be interposer wafers, and there definitely will be substrate panels. All of that has to come together, and they it was mentioned that right now we are in an intra-company ecosystem where one department of the company sells components to another one. But where it's headed is that there will be trade going among companies on putting these assemblies together. So typically what happens is for these components, if they are incoming as pieces of silicon like chiplets, there has to be some kind of a understanding of defective parts per million. And then, which basically means that there will be defective components coming in no matter what. So that puts a lot of pressure on the final test and system level test as I defined it. Because from business point of view, you just really cannot ship bad parts to the customer. You have to catch them all. So you have to not only just catch the assembly structural defects, but you also have to catch if there was any escape in the components. Commonly done already in printed circuit board, but these complexities are now shrinking in the world of multi-chiplet integrated circuits. So a few words on the testing aspects of the design and manufacturing. We obviously now need to think deeply at a very early stage about the design for test. And it's next to impossible to do it otherwise because cost just does not make sense. So we have to think about obviously the contact probes and stuff and the package part tests that we do on chip incoming components and possibly even burn-in and final test. And then it goes into the next input, which is the integration piece of it. And in the integration piece, like I mentioned, component tests are great in terms of inspection or warranties via defective parts. But what's critical really is system level final package test that is going to guarantee the supply to the follow-on customer. And one lesson that we had learned, there was a lot of debate we did on, do we do burn-in? When do we do burn-in? Do we do it in the components or do we do it after final assembly? It becomes pretty complicated after final assembly, but it may not be avoidable. So, individual results may vary, but it's from cost point of view, if you can avoid it or push it back, it's a cost saver. So I'll just say a few things about what we learned in terms of the testing of these chips. So basically, we broke it into three different buckets. There was contact probe for chiplets and active interposers, and the probe cards and the testers that go into these fine pitch bump type of testing hardware, they're quite expensive, and that needs to be a consideration. When we go to the system level test after packaging, we generally go through a sequence of stuff, which was obviously we want to check the structural quality issues of opens and shorts, and then subsequently start going into more and more functional things such as IDDQs, firmware, system level function tests, radio frequency tests, and whatnot. You may notice I did not put the scan stuff in here. And the thing is, it's a luxury for a startup to actually get components built to your specification. But with the industry going in this direction, the components will likely have support for new and upcoming IEEE standards. So that will be a necessity. And when you go to reliability tests, there's some really strange problems that come in this archaic manufacturing of packaging, which are related to solderability, reflows, and all of that stuff that needs to be worked out. So that's an important one. And then there is a whole gamut of other reliability tests that come into picture for early life failure and later life failure. So all of these different tests need to be understood very early on by the architects and designers, and they need to kind of like plan for it. And the questions related to, do we test on the bumps or do we put sacrificial pads, is a important one and one solution to it. So I'll tell you a couple of things. It's just a thought exercise here on doing high-level calculation of why test is so important from the cost point of view. So very early in the design of these type of assemblies, we as designers typically think about verification and DFT, and we add all kind of interfaces. JTAG is usually a must, right? But the newer ones are great. And then we start thinking about, okay, what might happen when these materials are moving, and then we have some issues related to, say, missing solder balls, right, or something of that nature. So visual inspection becomes kind of like important. And after assembly, we do have something like at least go through some inspection and then focus on system level reliability. So let's do a thought exercise. So let's say that there is a system that has 5 components, 4 chiplets, and we somehow manage to negotiate a defective parts per million of like less than 100 out of a million. And if we take all of this together and we believe in the allegedly 99% assembly yield, what you will notice is that in a worst case scenario, when you have totally non-overlapping faults, there will be about 500 bad components that will be produced out of a million, right? And since you want 100 defective parts for incoming, the customer may be okay with 500 bad out of a million, but the key is that system level test or the final test has to make sure that it catches those issues. Now, obviously, this kind of testing thinking does not account for pairwise faults. So let's say if there's a pairwise fault between chiplet 1 and chiplet 2 after they get assembled due to some design sensitivity, that is a design problem, that is a systematic problem, and needs to be worked out at the design stage. So with that one, let's start thinking about the system level final tests and see what are the main components. And this is what we had learned, that with the system level test, would like to find obviously the assembly defects. If we could somehow repair those, we would. And I'll show you the example of how we were actually doing a repair for it. And then we wanted to validate all the power down conditions that the currents as were spoken for actually being manufactured. And we go through all kinds of IDDQ combinations across various components. And the next one, generally in this system level test, is validation of the functionality, which is to load the system level debug firmware, do a boot up, check for pairwise communication across various components in chiplets, and then start doing outside loopbacks, eye scans, and things of that nature. And obviously, our goal would be to give it to the customer. So we would try generally to find what is the customer application. Maybe we can run a bare minimum version of it. So as you can see, the system level test starts becoming really kind of like expensive as you throw in more and more things in it. But the goal would be that eventually we stabilize the system level test such that we can only get away with item number 2 and don't even have to do functionality validation once the product is stable. So, and in the end, these tests typically would end up writing something into the integrated circuit. Might be repair data, it might be some kind of security signatures of type that customer needs. But that's the general anatomy of the system level test. So with that foundation, if we take a step back from a designer's point of view, we now need to start designing for a system level test. It's not just the scan piece, right? The scan piece is a must, right? But we need to go one level above it, right? So at a very high level, we start thinking about obviously JTAG needs to go to pretty much every component and potentially its upcoming variants. And then can we add instrumentation circuitry like eye monitors, current monitors, power monitors, things of that nature that can be made accessible to test engineering to make sure that the system at a very high level, the key components are working. We need to think about the power delivery network, and we need to hand that over to test engineers to test, in the sense that power issues are not just critical for the a functional version, but also, like Adam mentioned, during tests, right? And customer cares for the functional, so we have to expose some of that ability to the test engineers to make sure that power delivery does not have any catastrophic issue. And then die-to-die interfaces, they you can certainly go and test them pairwise and maybe put them all in a chain and test it that way. But the designers now have to make sure that test engineers do have access to maybe the key aspects of it. Right now we are talking about tens of gigahertz on the package, but where it's headed is we already have hundreds of gigahertz going to the outside world, and that all may be shrinking. So the way we did this test development, we actually sat on the bench and we developed system level tests in very early design, which is kind of like, early mock-ups of the system. So while the architecture was going on, we were developing tests for it. So by the time the product gets into an OSAT realm, all these tests are actually ready. So that's the kind of thinking that is needed at this point to design for system level tests. I'll say a couple of words about quality and reliability. And I know this is a very simplistic slide and I may be preaching to the choir, but for me it was a learning thing. So like quality, we all know is like, we have a specification and we are trying to make sure that the performance is according to specification. So one problem that we ran into was, how do we observe and debug all the failures? So because there's a lot of I/O connectivity, so we had to think pretty deeply about that one problem. It's like, we don't have the luxury now to go put a oscilloscope pin to pretty much to anything we want. So the architecture that we developed was thinking about observability and how to isolate failures. And we put in a lot of effort into all the other components like A versus B type of failure design. And when you go into reliability, it's basically quality over time, right? Because now you are thinking about these systems and in a way they might be going into harsh environments. So you have to guarantee some of the things that previously may not have been a worry at the chip level. So one challenge I'll say is, if you are using a backend factory to assemble the final product, there will be multiple reflows of some of these components. And those reflows start to have some really strange problems in certain cases. So we have to start thinking about those kind of manufacturing defects. And then, like I was saying, infant mortality is important with silicon in advanced nodes. But what starts becoming more important on the packaging side is later life failures due to wear out. So HTOL, for example, is an important test to plan out early because it takes a long time and it needs to make kind of like, mimic the actual usage of the product in the field. So that will be more favorite with advanced packaging than the burn-in piece. So that takes me to my next example. Abram, how am I doing on time?
You're doing good.
Okay. How much time do I have?
I've got about 10 minutes, including questions.
Okay. So I'll go through this one example, which is the Z-glue chiplet system. And some of these slides I had presented a few months ago at a 3D test conference. So I'll take this example and dig into a few of these concepts. Now, this is simplistic. This example is simplistic. It's basically a few silicon components on top of a active silicon interposer. And what you will notice that the active interposer is kind of like a bed of nails, and the incoming parts are kind of like overlapping on that bed of nails. That bed of nails, in the fine pitch resolution that you are seeing, is primarily designed for test. It's designed for test to make sure that there are no defects in terms of opens and shorts. But more than that, if we need redundancy, we have that. In a way, if you look at high bandwidth memory, you would see the design is kind of similar in a way that they're putting diversity of multiple bumps for one signal at times, right? So it was along the same concept. And you start digging into it. So the piece that is at the bottom, the brownish color, if you look inside, it's a piece of silicon. And this piece of silicon had a bunch of things related to the peripherals and power management. But the green part, which is the most important, that's the fabric that you look at the very top, is the one that does testability, and there are controllers and built-in self-test schemes inside of it. So what we had done there for our built-in self-test, we did put a bunch of things. We did put open short testing type of things. We did have the ability to turn things on and off, so we can measure the minimum current, the IDDQs. And then we could actually inject signal from one side on a trace that is totally unloaded and receive it on the other end. So not that we did that for every single one, but that was kind of like the foundation of test development, at least in the system level test, as I call it. We did have programmable probes, so you would notice that around the silicon chip, there are sacrificial pads. They were multi-purpose because they could communicate as I/O, and some of them were dedicated to test. So we actually did not test the interposer on all the bumps. What we did was we put a pretty inexpensive probe card and went from the edge of the interposer and started exercising pretty much all of these things that go all the way into, like, doing Kelvin probes, pull-ups, pull-downs, and bunch of other things that are pretty common in this type of area. So we have the ability to come from outside with a very conventional JTAG 1149.1 and then exercise our built-in test hardware. That would then do the heavy lifting of testing the chiplets on top of it. So there were a bunch of scan chains put into it to essentially parallelize and think about, not drawing too much inductive kicks and yet be able to test it in a reasonable time. So I'll give you an example here. So like I mentioned, that the fabric was a bunch of these pogo pin-like things, which are really copper pillars, and the chiplets were being assembled on top of it. And the built-in self-test can communicate with the external hardware via JTAG when it goes to testers, but when it goes to more like system level tests or final tests, we had exposed JTAG, SPI, I2C, and some of these other things were kind of like super helpful in running system functionality, especially when you start thinking about loading firmware and stuff. So here is an example of one of the tests. So this is like 5-6 years ago, and we were extremely worried about backend factory's ability to assemble things nicely And this actually ended up being much less of a problem because solder is great in terms of pulling everything together, but it's going to become problematic with copper to copper hybrid bonding again. So you may end up with situations where assemblies have some strange issues. That was one of those. But our tester underneath it knew what was the intention, and it had the ability to kind of like run a raster inside the chip to identify what's connected to what and maybe able to repair for it. So that was one of the foundation of the thing that we did, and that made it possible in a way to get to the final production. So the key thing that I want to mention here, like what I have said so far is that if you want to make a chiplet based product, proper test planning is key. So if I were to list item number one, that's item number one. The item number two is thermal, right? So maybe they're side by side. But without proper thinking about it at a very early stage by architects, it's difficult. And test planning is easier if chiplets are being developed in-house within one company. But when it goes to the multi-company collaboration, then we need to work on these gray box models or something that is acceptable to all the partners business-wise. So the testing of heterogeneous IC, like I said, SLT is the key. Known good die type of incoming components is a challenge because they're known good for something but may not be for everything. So somebody has to take the hit for it, but the final integrator has to make sure that no bad components, no bad parts go out to the customer just because incoming component was bad. Hence, SLT is critical. Pairwise faults, we have to find them in the design, and we have to work them out at bench and reserve testing only for manufacturing quality. That's from economics point of view is important. So one big question that has come to me in multiple times in last 5 years is the test cost. And I have my data and reasons to believe that test costs with proper thinking can be comparable to monolithic solutions. There is difference of opinion on that, but I have strong belief in that, especially if you design early on for test. 1149 is a great option for chiplets. 1838, 1500, all of those will make it awesome. So early life failures, see if you can work them out very early. Chiplet based is important, but obviously the architects have to think how they want to implement a based, and maybe memory is important, maybe packaging is important, maybe logic is important. So, but that's the key. So with that, I'm at the end of my talk, and I thank you for your attention. I'll take questions.
Thanks, Jawad. Got a couple questions here. So, I think the industry is used to, passive interposers in general, right? But here you mentioned, you're using an active interposer. So what sort of, I guess, test techniques do you kind of recommend, and what generally fails on these active interposers that we have to watch out for and, build in some sort of test strategy for specifically?
Right. So active interposer is a chip. It's simple way to think about it is it's going to have transistors. It may have advanced transistors. It may have some old ones. So you have to, number one, put scan in there for sure, right? And that active interposer has to be probed by itself before the assembly. That's one. The second one is if these interposers are going to then receive subsequent components on top of them, right? By the way, this applies to base dies and 3D IC interposers and backend factories, all of it. So that's where, like Adam was saying, 1838, they have thought through some of these problems of how you stack other chiplets on top. So you probably got to think about that test scheme as well. The other strange problem with these interposers, which is prevalent in 3D, in high bandwidth memory, the moment you go and put a lot of parallel wires or connections, uh, the moment you turn on switching, there are inductive kicks, and the power delivery network can be pretty stressed out. So you will have to think about testing some of that, though active interposers come out of silicon factories and their quality is much better than backend factories. So that helps a lot.
I guess as a follow-up to that, then, do you see kind of a need for double-sided probing for these active interposers, top and bottom?
If you ask me, sure. I think it's, but one thing I would do is, from economics point of view, reducing number of insertions and stuff is important. Mm-hmm. See if you can do a double-side probing just by doing a one-sided contact.
Yeah.
Right.
Sounds like a challenge for the industry.
Yep.
What typical failures do you typically see right now for chiplets or at these interfaces, and how do you guard against them?
Yeah, so two classes. Number one, maverick lots coming in for these components, and you then are confused, like what just happened? This component was working fine, but the supplier just supplied some bad parts. So that's one that's kind of like out of your control, but you have to catch it, right, and send it back, right? The second one is assembly related issues, and there is a whole bunch of that. I mean, I can probably maybe publicly talk about one of them, and that is copper pillar. They are great technology. You try to mold them and try to reflow them second time. There are horrible issues with the solder bridgings and things of that nature. Not that they cannot be worked out, but it becomes a test engineer's challenge in that sense. How you gonna find that? You can send them to FA lab and they will tell you, okay, let's change this, let's change that. But in the long run, these things potentially can come back, right? Yes. So that's where the manufacturing is improving daily, and but we always keep moving along technically. Like copper pillars were not enough. Now we are doing copper to copper hybrid bonding, and that has its own set of issues.
Yeah, I think this talks to your earlier question about reliability on multiple reflow cycles and things like that as well.
Right.
Causing degradation over time. All right, this is great. All right, thank you, Jawad.
I want to thank our sponsors once again who made this event possible and free of charge for everyone. So thank you to the sponsors, and if you have an opportunity to thank them when you are in contact with them, it is greatly appreciated so that they will continue to sponsor events. Walking through the sponsors, first and foremost is our diamond sponsor, Omcor, with their differentiators in technology, quality, and service. And in the emerald sponsors, we have Advantest, with the highest rankings from VLSI Research, and Synopsys, Silicon to Software. We'd also like to thank our Ruby sponsor, TechSearch International. And most importantly, we'd like to thank all of you for attending today, and I look forward to having everybody back tomorrow. So thank you and have a good rest of your day.